So far in this topic we've looked at the quantities associated with motion, and we've also looked at some graphs that are related to those as well. We're now going to take it another step further forward. And before we do that though, I just want to draw your attention to the fact that when we're looking at graphs of motion, they're basically just a representation of a mathematical relationship. And so what we can do with that with those mathematical relationships is to express them in an equation. So what we'll do in this video is actually derive those equations and give you a bit of a sense of where they come from. Having said that, the derivations that we'll go through here, they're not essential for you to be able to reproduce. They're just to show you that these equations actually are linked. Before we do that though, one key point, the equations of motion that we're going to look at are related to constant acceleration or uniformly accelerated motion. So by that, what we mean is that the acceleration or the value of the acceleration is going to be, uniformly accelerated motion. The value of the accelerated motion will be constant. So in other words, what we're really saying is that the value of A is going to be equal to a constant. So it's not going to vary across the motion that we're interested in. One other thing to be aware of here as well, we've got a number of quantities that we need to represent and the variables that we're going to use to represent them. Most of them you've already seen, but just to clarify and draw your attention to these quantities. Now, displacement and distance are effectively represented in the same way. So the symbol that we use for displacement or distance, as we've seen, is S. I'm going to write these equations without worrying about the vector notation, but you can also just, if you want to turn it into a vector equation, just add the vector notation to it. Velocity is the critical one here. We're going to split that up into the initial velocity or initial speed and a final velocity and speed. Now, we know that the variable that or the symbol that we use for velocity is v as a vector, and we also use that as v for speed as a scalar. We're going to use v now as the final velocity. We're going to use u as the initial velocity, and the units for both of those are meters per second. Now the reason why we use u, if you just think about it, v is velocity, go one letter previous in the alphabet and you get to u. So nothing particularly important there, just be aware that u is initial velocity, v is final velocity. Some other sources that you might see might have v with the subscript I for initial and v with the subscript f for final. So just be aware that there are some different representations. The next quantity there is acceleration, meters per second squared, using the symbol A, and the final quantity that basically sort of ties all those together is time, and units for time being seconds. Now, these equations that we're going to develop are based on these quantities, so you'll sometimes hear them being referred as the SUVAT equations. So that just refers to the quantities that we'll be dealing with. Now, the derivations themselves. These derivations, as I said, you don't need to memorize them. They're just useful so you can see how things are linked together. And to do the first equation, we're just going to go back and look at average velocity. I'll just indicate that with an AV down the bottom here so we don't get confused. Our definition for average velocity is displacement over time, or average speed distance over time. If you think about these quantities now though, with accelerated motion, it means that over time the average velocity, we can actually add up all the velocities across the motion and then divide by however many there are. In our variables that we've got here, we've only got two velocities that we really need to deal with. So we can just find the average of those two. So we can just do u plus v over 2. We can go through that in a bit more detail in class. I think I will, just to give you a better sense of how that works. But from there, we can rearrange that equation to write that distance is equal to the average velocity, u plus v over 2, multiplied by time. So there's the first one. Pretty simple, pretty straightforward. We will come back to that one in order to develop some of the other equations as well. Just to draw your attention to the fact that it is an important one, we'll highlight that. That is one of the ones that's in the data booklet. So the next one, again, we're going to recall a definition, and that definition is for acceleration. Acceleration is the change in velocity over time, and now we've got an initial and a final. We can say that that change in velocity is v minus u over t. So a is equal to v minus u over t. If we rearrange that, we get another equation of motion. So if we multiply by t and then add u, we'll end up with v is equal to u plus at. And again, that's another one that's in the data booklet. The next one is a little bit trickier in order to get it out, and it involves a bit of substituting. And by substituting, what I mean is that we're going to start off with s equals u plus v on 2, so going back to our first equation, and we're now going to substitute in this expression that we've just figured out for velocity. So this expression here is going to be replacing that variable v in there. So in the next line of working, we'll have s is equal to u plus, and I'll put square brackets around it to make it a bit clearer, u plus at, so there's the expression for v. That's all still divided by 2 and still multiplying by time. Now it's basically just a bit of algebra. If we remove the brackets inside, we get s is equal to 2u plus at all divided by 2 multiplied by t. I'm going to expand the brackets first, so we then end up with 2ut plus at squared all divided by 2. And one last step, if we've got 2ut divided by 2, the 2's will cancel, so that first term becomes ut, and the second term we've got at squared divided by 2. Instead of writing divided by 2, we'll write that as a half, and then multiplied by at squared. So there's the next one, s equals ut plus half at squared. The last one, we need to rearrange one of the equations. So from our acceleration, we had a is equal to v minus u on t, v minus u. We're going to rearrange that to give t is equal to v minus u on a. And we're now going to go back again to our an earlier expression that we saw, s on t, so average velocity, is equal to u plus v on 2, and we're going to substitute our time into that equation. Now before we do, let's actually cross multiply. We'll just make it a little bit easier to work with. So multiply the 2 up across this side, the t up across that side. We end up with 2s is equal to u plus v multiplied by t. Substitute in our value for t then, so we'd have u plus v multiplied by v minus u on a. So just substituting in for the value of t. Again, from here it's just a bit of algebra. We've got to divide by a on this side, so I'll multiply that up on the other side. So we've got 2as is equal to u plus v outside of v minus u. If I just change the order of this first bracket, so u plus v is the same as v plus u, the reason why I'm doing that is that we've now got, if you know your maths and you know your expansion, this is the an expression for the difference of two squares. So we can write that as 2as is equal to v squared minus u squared. If you're not quite sure about that, then just go through and expand the brackets and you'll find that that's the answer that you get. And again, last step then is to rearrange. Going through, basically it's just add u squared on this side. We end up with v squared is equal to u squared plus 2as. And that gives us our last equation of motion that we need to know. Now you might look at those and think, well, why do we need so many equations of motion? If you look at them, you'll notice in this equation there's no t, so we can use u, a, s and v to figure out some of the other quantities without having to worry about time. If we go up to this equation, there's no v, so we don't have to worry about final velocity there. We can use our initial velocity, time, acceleration and distance. If we go up to this one, there's no s, so we don't need to worry about a displacement in order to figure out something to do with velocities, acceleration and time. And for this one, there's no a. So basically, regardless of the scenario, there's an equation that you'll be able to use to figure out an unknown quantity. So we'll go through and do quite a few problems in class using these equations, and then, like I said, we'll use them in other scenarios as we move further forward as well.